Assalamu alaikum, dear students. I welcome you to the sixth lecture of probability and stochastic processes. In previous 5 lectures, we have covered set theoretic mathematical tools to analyze random events. Particularly, we covered those events where the sample space, the collection of all possible outcomes, was finite. The cardinality of all possible outcomes was finite. We took those sample spaces and made sigma algebras from them, which are collections of subsets of sample space. And then we assigned probabilities to those events, those subsets of sample spaces. We also covered different methods to combine events to make new events and then assign probabilities to those new events. In particular, we talked about joint probability, where the probability of two different events occurring together was discussed. We also discussed the concept of conditional probability, where some information is provided that reduces the region of uncertainty, and we can make better predictions because with the additional information of some event having occurred, the region of uncertainty is reduced and we can make a better prediction. These combined events, combined through the ideas of joint probability and through conditional probability, were used to find unconditional probability of events indirectly through the concept of total probability, in which the unconditional probability of a given event A was found as sum of different products, and in each product there was a conditional probability of a part of sample space having occurred, and then all these partitions were combined to make the unconditional probability of a given event. Let's continue to talk about these ideas of total probability, conditional probability, and joint probability to have a good understanding of these concepts. Coming back to the concept of joint probability, we know that joint probability is probability of two events A and B occurring simultaneously. It's possible that the random experiment is performed and the outcome sometimes belongs to an event A and sometimes belong to event B. And there are certain outcomes when they occur, they belong to both A and B. That is, event A and B have some common intersection. So if the outcome belongs to that common intersection, we say both events have occurred. And we are interested in the probability of them occurring together, or their joint probability. We have also talked about independence. Let's combine these two events and find out that if two events are independent, what is their joint probability? If you look at this slide, it shows that we have two events A and B and they are independent. That is, probability of A given that B has occurred is same as probability of A having occurred independent of the information that B occurred or did not occur. If you take this formula and expand this, you will find that the joint probability of A and B, which is probability of A intersection B, is equal to multiplication of unconditional probabilities of A and B. And if this is not true, if the two events are not independent of each other, then you cannot find their joint probability by multiplying their unconditional probabilities, because occurrence of one event changes the probability of the other event. This will be clear if we look at that example we were talking about, where we have two sacks, and in each sack there are 3 green and 2 red balls. So let's define two events A and B. Event A is that if we take a ball from the first stack, it is green. And event B is that if we take a ball from the second stack, it's also green. So the joint probability is that we take one ball from one stack, another ball from the other stack, and both of them are green. What is the probability of that occurring? If the two events are independent, that is, they are performed jointly or one after the other with replacement, then it's easy to see that the probability of event A is 3/5 and probability of event B is also 3/5. Hence, the probability of them occurring together is 9/25. But if we perform this experiment as a cascade of two experiments without replacement, that is, we take out one ball and then do not put it back and take another ball, then if we talk about joint probability of the two balls being green, then the first ball being green changes the composition of the sack, and then the probability of event B, that is the second ball being green, is not equal to 3/5, but it is 2/4, because there are 4 balls, 2 are green, 2 are red. So the probability of these two events occurring together is 3/5 times 2/4, which is 3/10, which is larger than 9/25. So the first event, that the ball was green, has increased the probability of the ball being green on the second occasion, and we get a different value of joint probability. Let's take another example. Suppose the Pakistani cricket team is having trouble with its opening batsmen. None of them is performing as expected. So the national team selectors have been provided with 8 prospective candidates for opening batsmen. 3 out of these 8 players are left-handed and 5 out of these players are right-handed. All of these players are very capable batsmen. Furthermore, all of these are very well connected with the people who move in the corridors of power. So, to make a fair selection and not to antagonize any of those influential people who have made very persuasive calls, the selectors decide to hold a random draw. They are going to choose 2 players out of these 8 candidates, and this selection will be random, and furthermore this will be a selection without replacement. I hope you are able to see that once you pick one person out of this 8 to be the first opener, the one who is going to face the first ball, you cannot have the same person occupying the second slot. So you have to pick another person out of the remaining 7 people. So this is a random draw without replacement. You cannot have Salman Butt and Salman Butt going as openers. So if it's going to be a random and fair draw, what is the probability that both of these openers will be left-handed? We have found that 3 players out of these 8 candidates are left-handed and 5 are right-handed. If we do not make this distinction, then the first choice will be out of the 8 possible players, and the second choice will be out of the 7 players. So the total choices when you are picking 2 players out of 8 is 8 into 7, 56. Now, if you are supposed to get 2 players both left-handed, then the first choice will be out of the 3 left-handed players, and the second choice will be out of the remaining 2 left-handed players. So total number of ways you can pick 2 openers, both of them being left-handed, is equal to 3 into 2, 6. So probability of having 2 left-handed openers is 6/56, which is approximately 11%. This is not a big number. So if you happen to see 2 openers, both of them left-handed, you should be rest assured that our selectors do not hold random draws for selection of place. These kind of problems where we make subsets out of a larger collection is dealt with in a special branch of mathematics called combinatorics. In combinatorics, we are provided with a source set, and from this source set, we have to have a smaller subset and take this smaller subset and find out how many ways you can take this smaller subset. When you take out a smaller subset from the source set, there are different ways that you can arrange the entries in this smaller subset. The first method is called formation of words from a given alphabet. If you see in this slide, I have shown a source set to contain 3 alphabets A, B, and E. If you use this source set to make words of English with 3 letters, you can make AB, B, ABE, ABA, and other words from this source set which contained only 3 letters. One thing to note is that there are repetitions. In B, there are 2 E's. So if you have a source set of alphabets and you are making words out of them, you can have repetitions. Actually, you can take one alphabet and repeat it as many times as you want to get a certain word. And there are other combinations of alphabets which have many applications. For example, if we take our alphabets to be binary numbers 0 and 1 and make 16-bit binary words out of them, you can have 2 raised to power 16 possible 16-bit numbers. If you look at this slide, you will see other examples of words being formed from alphabets. Suppose your alphabets are decimal numbers 0, 1, 2, 3 up to 9, and you are making 6-digit decimal numbers. So every location in this 6-digit number can be either 0, 1, 2, 3 or 9. So there are 10 ways to choose each digit out of the 6 possible places. So the total number of 6-digit decimal numbers is 10 raised to power 6 or 1 million. This is exactly equal to the total number of prize bonds in a series. So when you are buying one prize bond in any series, you are buying one out of a total possible of 1 million prize bonds. So probability of you winning the biggest prize is 1 out of 1 million, or just 1/1,000,000th part of 1. There are other examples on this slide. For example, if you are going to form 4-digit English words, meaningful or meaningless, and since there are 26 characters in English alphabets, you can have 457,000 approximately words which are length 4. This is important for the case of formation of passwords. If somebody has selected a 4-letter English word for his password, all you have to do to break this password is that you try all possible approximately 457,000 4-character English words, and one of them will be the unknown password. There are a few things that you should notice about formation of words from a source set of alphabets. One is that we are forming vectors, because in sets repetition is meaningless, but in vectors each location has its own importance and you can have the same element at different locations of the vectors. Second thing is that the cardinality of the source set, the total number of alphabets available, could be smaller than the size of the words that we are going to form. For example, we can use binary numbers 0, 1 to make 16-bit binary words. Similarly, we can have decimal numbers 0 to 9 to have a 25-digit big decimal numbers. So when you are forming words from a source set which is called alphabets, you are doing selection without replacement. You pick a number, put it in the first slot, and use that number again because you have put it back into the collection of numbers that you can use. So the largest possible subsets, the largest number of possible subsets of a certain length that you can make out of a certain alphabet is through formation of vectors and with replacement. And if you have n as the total number of alphabets available and you have p as the total number of places where those alphabets will be put, then the total number of vectors that you can form is n raised to power p. So if you have two binary digits 0, 1 and you are making 16-bit words, you can make a total of 2 raised to power 16 possible 16-bit binary words. The next method that we are going to discuss, where we take a source set, take elements from this source set and form vectors from these elements, but with one new condition, that we are not allowed to replace the picked element back in the source set. So we are making vectors without replacement. Suppose you have 3 alphabets again, and if you look at this slide, I have used A, B and C as new alphabets, and I am going to make length 2 vectors out of that, but without replacement. I cannot have A comma A as my vector. If I have picked A, then I have to either pick B or C for the second slot. And it's easy to see that I can freely pick the first element. So I have choices of either A, B or C, 3 choices to pick the first element. And once I have picked the first element, I have only 2 choices to pick the second element out of the remaining 2. So total number of length 2 vectors that can be formed from a source set with 3 alphabets is 3 times 2, 6. Suppose you have a source set which contains m elements and you are forming m length vectors from it. Then you have a choice of m when you are filling the first slot, but you have a choice of m minus 1 when you are filling the second slot, and so on and so forth. So if you have a source set which contains m elements and you are making vectors of length m without replacement, the total number of such length m vectors is equal to m factorial. This is very important result and will be used in the next topic we are going to cover. Before we go to that topic, there is one important observation about formation of vectors without replacement. It's obvious, but it is worth mentioning anyway. If you have a source set which contains m elements, you cannot form a vector of length larger than m if you are taking elements from source set and putting in this new vector, and you are not allowed to do the replacement, because by the time the mth slot is filled, you have run out of elements in the source set. So this formation of vectors of length m from a source set with cardinality m is called permutation, and total number of permutations are m factorial. If you have a source set of m elements, you can permute them m factorial ways to get vectors length m. The next thing that we are going to discuss is called combination. It is different from this permutation because in combination we form subsets from a given source set. So given a source set of cardinality m, you take a few elements out of it and form a subset, and in this subset all these elements are equal. There is no first, second, third. They are in a set, not in a vector. So there are fewer ways to form sets. For example, if you have a total of 16 players that are going with Pakistani team to a foreign country, then you can pick a a certain number of teams out of them, each team being 11 players. And then when you have this team which is actually going to play the game, you can have permutations, the batting order, where you put one of those 11 players as the first person who is going to face the first ball, another person the second player, and so on and so forth. So if you are forming subsets from a given source set, you can do it in fewer ways, and if you are forming vectors from a source set, you can do it in more number of ways. And the difference is exactly the number of permutations that you can have from a given subset. So if you have a total of 16 players, you can form a certain number of subsets which we can call the actual playing team, and from this actual playing team of 11 players, you can have 11 factorial different batting orders. So the formulas for permutation and combination are there in your textbook, you can see, but important thing to notice is that if you are forming words from a given alphabet where words are considered vectors and repetition is allowed, you can have a very large number of ways of making these words. And if you are not allowed to do repetition, you can pick a number and use it and have to use another number for the next location. You are doing permutations and you have fewer number of ways to get such sub-collections. And if you are forming subsets where you pick a few elements out of the source set and put them in a set and they are all equal, then you have even fewer number of ways to make such subsets. All these things are covered under combinatorics. Let's look a few examples where combinatorics plays its role. Suppose before the Pakistani team goes on a tour, 21 players are called in a training camp. The purpose of the training camp is to select 16 member squad. What is total number of ways that you can make this 16 member team at the end of this training camp? So you can make a total of more than 20,000 teams of 16 players out of the 21 players who participated in the training camp. But this is not how the teams are selected. Some players are guaranteed a spot in the team because of their past performances and other factors that we cannot talk about. So suppose there are 9 players who have assured their place in the team because of their past performance. And the real purpose of the training camp is to select remaining 7 players out of the 12 players that are the candidate for these 7 slots. So how many ways can you pick 7 players out of 12 candidates with uncertain future for their aspirations? It turns out that you can pick 7 players out of 12 candidates in 792 different ways. And we can extend this example by saying that out of those 12 players, there are 4 who are from the same city and really good friends. So what's the probability of all 4 of them making the team? You can find the total number of ways these 4 players can take their spot in the 7 available slots and divide that by 792 and get the probability of those 4 good friends making to the Pakistani team. The next example where we will find the application of combinatorics is the famous birthday problem. It is proposed in this way that suppose there is a room and there are n people in the room. It could be a classroom with students or guests in a party, but there is a collection of n human beings randomly chosen without knowing their birthdays. And once you have chosen these n people, what is the probability that at least 2 of them will have same birthday? They could be born in different years, but the month and the day of the month should be same. This is a nice example and it needs careful modeling. Suppose there are n people and the total number of days that we are considering is 365. So we are excluding 29th of February and assuming that the year is 365 days. And there are n people and we are interested in this probability that two of them, at least two of them, have a common month and day that they were born. So which is the source set and which is the destination set? If you make this collection of 365 days as source set, then you are fine. If you do the other way around, you won't be able to solve the problem. So our source set is 365 days, 1st January, 2nd January, all the way to 31st of December. We don't mention the year and we don't include 29th February. This is the source set and these are n people. So what's the total possible number of ways that these dates, the elements of these source set, can be assigned to these n elements? We include the possibility of these n people having the same month and day that they were born. So to form this vector, you make these people stand in a line with alphabetically descending order according to their last names. So you have this vector and then you take dates out of this collection of 365 days and assign to these people their birth, month and date. If you do so and if you allow the possibility of repetition, that it's possible that 2, 3 or more than 3, possibly all people can be born on the same day, then you are forming a word from alphabet, and total possible number of ways that you can do that is 365 raised to power n if there are n people. Now look at that special event where none of them have a common birth, month and day. Actually, we are interested in the other event, that is that at least two of them have common birthday. But we are considering this special event which is complement of that all these people have different birthdays. So if that's the case, then you pick one date assigned to the first person, and since there is no common birthday, you cannot take this birth date and assign it to another person. You have to pick another one. So this is where you are forming vectors without repetition, and total number of ways to do that is 365 factorial divided by n factorial, or permutation of 365 length source set into n slots, and the probability of none of them having the same birthday is permutation of 365 with n divided by 365 raised to power n, which is the total number of ways these dates can be assigned to these people with possibility of repetition. These ideas will be more clear to you if you look at the next slide. This slide has a graph of probability of having at least two people with the same birthday as the number of people in the room increases. And you can see from the graph that this probability of having a common birthday approaches unity much sooner than most people usually expect. If you look at this graph, you will see that if you have 20 people, the probability of at least two of them having the same birthday is 41%. And if you happen to have 40 people in the room, then probability of at least two of them having the same birthday is 89%. There is one tricky case though. If there are more than 365 people in the room, then probability of at least two of them having the same birthday is 1. It's a certain event. You can look at another variation of this problem where you have n people in the room and you try to find if two of them or more than two of them were born in the same month. In the previous example where we were interested in month as well as day of the month, we assumed that it is equally likely for a person to have been born on any of the 365 days that we were considering. If you are solving this problem where you are trying to find the probability of 2 or more people having been born in the same month, you should be careful, because it's not true that a person is equally likely to have been born in any month, because February is shorter than many months which are 30 or 31 days. And secondly, there are certain times of the year when our maternity wards are more actively contributing towards population explosion. The last example that we are going to discuss where combinatorics play an important role is called the problem of stuffing envelopes, or the problem of inept and careless secretary. Suppose you are a big officer in an office and you have decided to send a few letters to important people, your clients, your business partners, or any other set of important people. So you prepare n letters if you have n such people that are going to receive these letters. So you type n letters and then you type n personalized envelopes, and then you give these letters and these envelopes to your secretary and ask him or her to stuff these letters in the envelope so that a letter addressed to a certain person is stuffed in the same envelope which bears his name. But that secretary working in your office under a well-publicized internship program has no hope for a bright career in this office automation. He is careless, he is demotivated, so he randomly fills these envelopes. He takes n letters and puts one letter in one envelope, but without caring what is the name on the letter and what's the name on the envelope. Now the question is, if you have n letters and n envelopes, what's the probability that a certain number of letters will be correctly addressed and they will reach their intended recipients? Sometimes this question is asked as a tricky question in interviews, where the interviewer asks the candidate that if this is the scenario, what's the probability that one letter will be misplaced, one letter will be misdirected, and all other will reach their intended destination? What's the probability of that? The answer is 0. It's not possible to have n letters and then just have only one misplaced letter. You have to have at least 2 so that you can swap the 2 letters and 2 envelopes, and at least 2 will not reach the desired recipient. But it's possible that only one letter reaches the desired recipient and every other letter reaches the wrong recipient. That can be accomplished if you have n letters properly stuffed, take that letter and mix the others. So this will go to the desired recipient and all these will not go. So how does combinatorics can be used to solve this problem? Since we have n letters and n envelopes, we can think this problem as a permutation. So you take your n letters, pick one, and then you have a choice to put this letter in any of the n envelopes. Once you have put it in one envelope, you put the envelope aside, and then you take the next letter and you have a choice of n minus 1. You can put the next letter in n minus 1 envelope, and so on and so forth. So total number of ways that these letters can be stuffed in different ways is n factorial. So what's the probability that a certain sub portion of this collection of letters will not reach the desired recipients? Let's start with 2. So what's the probability that 2 people will not receive their intended letter? You can look at this in this way that you have n properly filled envelopes. And then how many ways can you pick two envelopes out of this collection and swap the two letters? Of course, you can pick your first letter in n possible ways, and having picked the first letter, you can pick the second letter in n minus 1 ways. So total number of ways that you can pick two envelopes out of a collection of n correctly filled envelope is n into n minus 1. Having picked these two envelopes, you can swap the contents and these two people will not receive their own letters. You can find probabilities of other events like exactly 5 people not receiving their own letters, which will be equal to 1 over n minus 5 factorial, or exactly 1 person receiving his own letter and others not receiving their letters. So far, we have applied the rules of combinatorics and set theoretic analysis to solve some real-life random problems. The kind of applications that we discussed only dealt with simple rules of combinatorics. You can certainly look into your textbook and find more complicated and more challenging problems where combinatorics play an important role. So we have covered the basic, and I hope that you will consider this as a starting point and go deeper and solve more challenging problems of combinatorics. The last thing that we are going to discuss in today's lecture is very important, and it is called Bayes' rule. This rule allows us to make certain assertions about an unknown in a random experiment where the information about the unknown is only indirectly revealed to us. I'll try to motivate you with an example. And I'll take the example of Lahore, even though the example is applicable to any big city of Pakistan. Suppose you are talking to a friend of yours and he tells you that he has an uncle who owns a 1,000 square yard house in DHA Lahore. DHA Lahore is a posh community of rich people. So with this information that the uncle of your friend has a big house in DHA, you can make a certain guess, a certain assertion about the financial net worth of that uncle. Of course, he is rich considering the going prices of big houses in DHA. But can you make a guess about professional background of that uncle? I posed this problem to many people around me, and most of them said that most probably that uncle is a Pakistan Army officer. It's amazing that so many well-informed people of our society can make this statement. And why this statement makes sense will be obvious in a few minutes. So, in analyzing this problem, you should consider what is the random experiment, what are conditional probabilities, what are direct pieces of information, and what are indirect pieces of information which reveal this common belief that if a person owns a big house in DHA, he must be an officer in Pakistan Army. All these things are combined together in Bayes' rule, and if you look at this slide, you will see the equations which are involved in this Bayes' rule. We already talked about the total probability, where the unconditional probability of an event A is found indirectly through a summation of conditional probabilities conditioned on a collection of sets B1, B2 and Bn, where this collection forms a partition of the sample space. And we know a certain probability which is called a priori probability, which is probability of a certain event occurring given that the event belongs to one member of this partition. It is called a priori because we know it beforehand that if the outcome belongs to this partition, then the probability of a certain event occurring is this. A related idea to a priori probability is the idea of a posteriori probability, which states that given an event having occurred, what is the probability that this event occurred through a certain partition of the sample space. These ideas are combined together in Bayes' rule, and if you look into this slide, you will see that probability of an event A, the unconditional probability, is obtained through summation of a priori probabilities of this event occurring given on certain partition of the sample space multiplied by the probability of that partition having occurred. And if you look at the formula of the conditional probability, probability A given Bn, you can have this as probability of joint even A and Bn divided by the probability of Bn. From this formula, you can take out the joint probability of Bn intersection with A as multiplication of probability of A given Bn times probability of Bn. But if you start with the other probability where given that event A has occurred, what is the probability that a certain partition Bn occurred, you can look at this formula and expand it, and you will get this as probability of Bn intersection A divided by probability of A, and you can replace this intersection probability with the above formula to get the Bayes rule, which says that probability of a certain partition occurring given that a certain event has occurred can be found from the unconditional probability of that event and the a priori probabilities of that event occurring given a certain partition has occurred. These ideas will be clear if we take a concrete example. The example is shown in next slide, where we take a university, a Pakistani university, where a system of co-education is followed. So in this university, there are female students and male students. And the experiment is that you pick a student randomly out of the total population and see if that student is colorblind or not. It is a well-known fact that boys are more likely to be colorblind than girls. Actually, boys are more susceptible to many other ailments compared to girls, because in the early life of a male fetus, it has to go through a tortuous transformation which leaves it very weak for the whole life. So a boy is more likely to be colorblind, and let's assume that if you pick a boy out of a collection of boys, then 10% of the boys will be colorblind. And if you pick a girl out of a collection of girls, then 1 out of 30 girls will be colorblind. Then, if you pick a student from that university, what's the probability that he or she will be colorblind? The answer depends on this fact that out of the total population, how many are boys and how many are girls. Suppose 70% of student population is boys and 30% is girls, a typical ratio of boys and girls in our universities. So what's the total probability of this event that a randomly picked student is colorblind comes through two partitions. The sample space is whole student population, and it is divided into partition of B1, which is boys, and B2, which is girls. So what's the probability that a randomly picked student is a boy? Of course, it is 7/10 or 70%, because 70% of the student population is boys. So this is probability, the unconditional probability of B1. Similarly, the unconditional probability of B2 is 30% or 3/10. Then, if it is a boy, then 10% probability is that he will be colorblind. And if it's a girl, then 1 out of 30 chances are that she will be colorblind. So what's the total probability of this event, that a randomly picked student will be colorblind? It is probability of B1 and then multiplied with probability of a boy being colorblind from the total population. So it's 7/10 times 1/10 plus probability of B2, which is 3/10 times the probability of a girl being blind, which is 1/30. So if you combine these two, you will get the answer, which is that there is an 8% chance or probability of 0.08 that a randomly picked student will be colorblind. Now, the real application of Bayes' rule goes like this, that we pick a student randomly and we find that the student is colorblind. What's the probability that the student under consideration is a boy, and what's the probability that the student under consideration is a girl? So this conditioning event is that we have found a randomly picked student to be colorblind, and we are investigating if this is true, then what's the probability that this student is a boy coming from B1 partition or a girl coming from B2 partition. So this is the application of Bayes' rule, and by putting the values in the formula for Bayes' rule, we find in this slide that probability of a randomly picked student who is colorblind to be a boy is 7/8. This 7/8 is a large number, and this reflects two things. One is that boys are more likely to be colorblind than girls, and secondly, in that particular university, 70% of the student population is boys. So there is an overwhelmingly great chance that a randomly picked student who is colorblind is a boy. These ideas will be more clear if you look at the next slide, which graphically shows the relationship of these partitions, the conditional probabilities of a boy being colorblind and a girl being colorblind, and the total probability of the event that a randomly picked student is colorblind. In this slide, the big rectangle represents the sample space, the whole student population. This is divided in two partitions, B1 and B2, and the areas of these regions marked by B1 and B2 are approximately 70% and 30% of the area of the big rectangle. So the areas in this figure are representing the probabilities. So B1 partition, the partition of boys, is big, and partition B2, the partition of girls, is small. Then the lower portions of these partitions represent the percentage of students who are colorblind. For partition B1, larger portion, about 10%, represent those 10% boys which are colorblind. And for partition B2, a smaller portion, probably around 3.3%, represents the girls that are colorblind. And the total green area from the left partition as well as from the right partition represents the event A, which is that a randomly picked student is colorblind. And in this particular case, the probability of event A happens to be around 8%. Now, given that event A has occurred, given that randomly picked student is colorblind, what is the probability that it came from partition B1, and what's the probability that it came from B2? If you consider event A to be conditioning event, that is, given that the randomly picked student is colorblind, what is the probability that the student belongs to B1 or student belongs to B2? Then this region A, the total green area, represents the new reduced region of uncertainty, and this is our restricted sample space. And the left hand green area occupies a much bigger portion of this restricted sample space compared to the right-handed green area. Hence, probability of a student coming from B1 is much larger. Actually, it is 7/8, and probability of a randomly picked colorblind student being a girl is only 1/8. These numbers will change if the proportion of boys and girls in a university are different. For a certain university where there are equal number of boys and girls, the a posteriori probability of a randomly picked colorblind student being a boy will be less than 7/8, but still higher than the a posteriori probability of a randomly picked colorblind student being a girl. Can you guess a situation where these two a posteriori probabilities will be equal? It turns out that if there is a university where girls outnumber boys by a ratio of 3:1, that is 75% girls and 25% boys, then a randomly picked colorblind student is equally likely to be a boy or a girl. And lastly, if you are considering a women's only university like Fatma Jinnah University, and there you pick a student randomly and find that student to be colorblind, the probability of that student being a boy is of course 0, because there are no boys in there. You can work this out by using the formulas of Bayes' rule. So in today's lecture, we extended our discussion of set theoretic analysis of random events. We talked about conditional probability, joint probability, combinatorics, and application of these ideas to Bayes' rule. Bayes' rule is very important, and we started one example and we could not finish due to shortage of time. And in the next lecture, we'll start with discussion of Bayes' rule again, and that example of a person owning a house in DHA, most likely being an army officer. Till then, I wish you goodbye. Thank you. Assalamu alaikum.